Humanity's persistent aspiration to grasp the fundamental structure and origin of the cosmos has defined much of its intellectual evolution. From ancient metaphysical conjectures to the formulation of contemporary cosmological models, the endeavor to decipher the totality of existence has remained an intrinsic trait of conscious inquiry. The recent revelations emerging from the James Webb Space Telescope represent a categorical upheaval in this historical arc. These observations, surpassing all previous thresholds of resolution and depth, have not merely expanded empirical data, they have begun to dismantle the foundational certainties on which modern astrophysics and cosmology rest. What the James Webb Space Telescope has transmitted from the most remote and ancient corners of the observable universe constitutes more than an incremental refinement of existing paradigms. It signifies the surfacing of anomalies that radically conflict with the presuppositions underpinning the standard cosmological model. When images arrive exhibiting massive galaxies with structured organization existing less than 200 million years after the proposed origin point of the universe, a fundamental contradiction is introduced. The inflationary model, which posits a rapid expansion of space immediately following the Big Bang, cannot accommodate the emergence of such well-defined galactic structures within such an abbreviated temporal framework. Theoretically, at this stage in universal evolution, only amorphous clouds of hydrogen and helium should be detectable. Random, thermally turbulent, gravitationally unstable. And yet, what is observed are galaxies with mass, rotational dynamics, and structural integrity reminiscent of the Milky Way. This discrepancy reveals a deeper problem. The apparent chronological and structural maturity of these early universe objects violates both relativistic and thermodynamic constraints. If the universe was indeed formed approximately 13.8 billion years ago, and if light from these galaxies has traveled for more than 13 billion years to reach our instruments, then the conditions under which such entities could have emerged must be fundamentally reassessed. Either the timescales used to model cosmological evolution are incorrect, or the physical processes governing early structure formation are not what contemporary theories assume. Moreover, the discovery of the exoplanet HIP 65426d, captured through direct imaging, amplifies the incongruity. This celestial body, possessing a mass 7 times greater than that of Jupiter and located at a distance 3 times farther from its star than Neptune is from the Sun, orbits a stellar body aged merely 15 to 20 million years. According to current models of planetary accretion and stellar evolution, such a configuration is implausible. The absence of a protoplanetary disk, the premature age of the host star, and the immense mass of the exoplanet combine to form a scenario irreconcilable with known mechanisms of planetary genesis. If such contradictions were isolated phenomena, they might be interpreted as statistical outliers, temporary inconsistencies, or artifacts of instrumentation. However, the James Webb Space Telescope's data set demonstrates a pattern of structural, chronological, and energetic deviations repeated across various observed sectors of the universe. Patterns in the galaxy, NGC 1365, suggest rotational and morphological behaviors inconsistent with gravitational models derived from Newtonian mechanics and general relativity. Symmetrical formations, such as the so-called perfect Einstein ring formed by the light of galaxy J418, align with a precision that implies a geometrical intentionality, far exceeding probabilistic expectation under conditions of cosmic randomness. The gravitational lensing phenomenon responsible for Einstein rings is well documented and theoretically robust, grounded in the general theory of relativity. However, the precision and circularity of this specific ring challenge the notion of natural variation. The underlying alignment necessary to produce such an effect, spanning over 12 billion light-years, suggests either an extremely rare cosmic coincidence or the presence of a deeper organizational principle embedded within the very structure of space-time. If the latter is true, it would mean reinterpreting the fabric of the cosmos not as an entropic and stochastic environment, but as a domain potentially characterized by latent order, pattern, and recursion. This reconsideration leads inevitably to a confrontation with one of the central tenets of modern physics: the existence and function of dark matter. Constituting, theoretically, over 85% of the matter in the universe, dark matter has long been posited as the explanatory variable for gravitational behaviors not accounted for by visible matter. Yet, observations conducted via the James Webb Space Telescope have begun to subvert this assumption. In analyzing the rotational dynamics of galaxies and the bending of light around massive clusters, data has emerged suggesting that these phenomena can be explained without invoking invisible mass. Alternative models, such as modified Newtonian dynamics, AMOND, propose adjustments to gravitational laws at galactic scales. These models, long relegated to the periphery of astrophysical theory, now find themselves increasingly relevant. If MOND or similar frameworks gain empirical support, the implications are vast. The history of physics would have to accommodate the possibility that one of its most entrenched assumptions, that the gravitational behavior of galaxies necessitates the presence of dark matter, was, in fact, a miscalculation, a theoretical placeholder for unknown laws yet to be formalized. This is not a mere correction of numerical variables. It is the revision of foundational equations, the dismantling of explanatory scaffolds built over decades. Parallel to these structural reconsiderations is a more ontologically disturbing proposition arising from the detection of repeated geometrical patterns in spatial distributions across vast cosmic distances. Certain researchers have begun to speculate that the observed symmetries and repetitions are not coincidental nor naturally emergent, but indicative of a form of memory inherent in the cosmos itself. This hypothesis, drawing from quantum theories and speculative cosmologies, suggests that the universe might possess a form of historical continuity beyond causal linearity, a kind of structural memory that informs its present configurations based on previous states. The theory of cyclic cosmology emerges here as a serious alternative. Unlike the singularity-based model of the Big Bang, which implies a unique origin and linear temporal evolution, cyclic models propose an eternal recurrence of cosmic epochs. The universe, in this view, is not a one-time event, but an iterative process, a series of expansions and contractions, each leaving residual imprints on the next. These imprints, potentially detectable as pattern recursions or structural echoes, would constitute evidence of a universe that not only exists in time, but remembers through time. Such a perspective undermines the linearity and singularity embedded in current cosmological narratives. It introduces the possibility that what we observe is not the first instantiation of cosmic reality, but a sequel, a reiteration, or a resonance of antecedent universes. The epistemological shift required to integrate this perspective is immense. It moves science from a domain of predictive empiricism to one that must grapple with recursion, resonance, and perhaps even intention. If configurations repeat not due to chance, but due to underlying laws or informational structures persisting across universal cycles, then the cosmos is no longer merely governed by energy and entropy, but by a form of metacausality. Within this context, the detection of rhythmic infrared signals from the constellation Fornax constitutes a further provocation. These emissions, not conforming to any known astrophysical process, display a repetitive frequency suggestive of intentional modulation. Although researchers refrain from explicitly invoking extraterrestrial intelligence, the regularity and precision of the signal differentiate it from stochastic or thermodynamic phenomena. If such emissions are indeed artificial, or at least organized beyond random dispersion, then the implications intersect not only with astronomy, but with philosophy of mind, metaphysics, and the theory of information. The reluctance to publicly ascribe these patterns to intelligence arises not from lack of imagination, but from methodological caution. Science, constrained by empirical verification and replicable observation, cannot accept conjectures about intelligent design or communicative intention without a framework for falsification. However, the repetition of certain spatial arrangements, the emergence of signal-like patterns in non-random frequencies, and the structural anomalies present in various galaxies suggest that the interpretive horizon must be expanded. If we are to consider the possibility that intelligence may not be exclusive to biological entities, but could be an emergent property of cosmic structures, then we must redefine our ontological categories. Intelligence would no longer be limited to cognitive processing in carbon-based organisms, but could manifest as pattern propagation, recursive design, or informational encoding across gravitational and electromagnetic media. Furthermore, the notion of an impending phase transition in the universe, as suggested by changes in the behavior of space-time and particle energy, raises the possibility that the laws of physics are not immutable constants, but context-dependent parameters subject to transformation. If the universe undergoes periodic shifts in its structural or dynamic foundations, then our current theoretical models are only locally valid, applicable within the temporal boundary conditions of the present cosmological epoch. Such a transition, were it to occur, would not necessarily be perceptible through cataclysmic events. It could manifest as a gradual drift in constants, a redefinition of relationships between fundamental forces, or a subtle restructuring of temporal perception. The possibility of an invisible and silent change in the very architecture of reality is perhaps more disquieting than any apocalyptic scenario. It implies that our observational tools, theories, and even modes of consciousness are embedded in a provisional system subject to change without notice. For over 4 centuries, the scientific method has operated under the assumption that the universe is fundamentally intelligible, governed by laws that are stable, discoverable, and universal. But the recent revelations from the James Webb Space Telescope suggest that this intelligibility may be an illusion, or at least a temporary condition. At this juncture, the scientific community stands at a threshold. It must decide whether to defend existing paradigms through increasingly elaborate ad hoc adjustments, or to initiate a methodological transformation commensurate with the anomalies observed. The latter path demands philosophical courage, intellectual humility, and an openness to radical reconfiguration of our understanding of existence. What is required now is not a new technology or a more powerful telescope, but a reorientation of thought. The data, already present, calls for interpretation beyond empirical measurement. It necessitates a synthesis of disciplines: physics, cosmology, philosophy, information theory, and even anthropology, to approach the universe not as a machine, but as a phenomenon whose full understanding may lie beyond the strictly material. The continuation of this reflection will delve deeper into the historical roots of cosmological theory, analyze the philosophical consequences of the universe as a potentially conscious or structured system, and explore the implications for human self-understanding in light of these discoveries. Stay engaged. What comes next may redefine not only what we know, but how we know. To confront the implications of the recent findings from the James Webb Space Telescope, it is necessary to re-examine the historical foundations of cosmological thought. The conception of the universe as a structured, law-governed totality emerged gradually from the dissolution of mythological cosmologies. In the pre-Socratic era, thinkers such as Anaximander and Heraclitus began to replace divine teleology with natural principles, This nascent rationalism reached a new articulation in the Hellenistic synthesis, where geometry and observation were combined to propose models of celestial mechanics. However, it was only with the emergence of Newtonian physics that a coherent, mathematically precise model of cosmic order was solidified. The Newtonian universe was mechanistic, deterministic, and infinite. Its foundational axiom was the universality of laws, gravitational, inertial, and temporal. This conceptual framework survived largely intact until the late 19th century, when observations and theoretical considerations led to a crisis. The constancy of the speed of light, the failure of ether-based theories, and the anomalies in black-body radiation initiated a cascade of theoretical innovations that culminated in the twin revolutions of relativity and quantum mechanics. Einstein's general theory of relativity replaced the fixed stage of Newtonian space with a dynamic, curved space-time. Gravity was no longer a force acting at a distance, but a manifestation of geometric deformation. Meanwhile, quantum theory introduced a probabilistic structure at the fundamental level, undermining determinism and replacing causal necessity with statistical distribution. These conceptual revolutions altered not only the mechanics of explanation, but the metaphysical assumptions underlying physical reality. The standard cosmological model that emerged from these developments, the lambda-cold dark matter model, integrated Einsteinian relativity with the observed expansion of the universe, incorporating dark matter and dark energy as necessary components to explain mass distribution and acceleration. For decades, this model has been refined and corroborated by a growing body of observations. Yet the data retrieved by the James Webb Space Telescope, particularly regarding early galactic formation, gravitational phenomena, and unexplained structural symmetry, threatens to unravel the consistency of this framework. What must be understood is that these anomalies are not trivial discrepancies. They do not merely require the adjustment of parameters or the addition of speculative particles. They demand a reconsideration of the presuppositions that structure the cosmological narrative: the nature of time, the linearity of causal development, and the assumption of randomness as the underlying condition of the cosmos. Consider, for instance, the implications of early massive galaxies existing less than 200 million years after the hypothesized Big Bang. In the Standard Model, the universe's earliest epochs were characterized by extreme density and temperature, followed by a period of rapid inflation, then gradual cooling, allowing particles, atoms, and eventually gravitational clumping to occur. The timeline from particle formation to galactic structure is measured in hundreds of millions of years. The appearance of organized luminous galaxies within this initial temporal window indicates either that the processes of structure formation are exponentially faster than current theory allows, or that these galaxies emerged from conditions not accounted for in the inflationary model. Furthermore, the presence of large exoplanets orbiting young stars without visible protoplanetary disks contradicts the accretion-based theory of planet formation. According to this model, gas giants form in the outer regions of dense disks of dust and gas that surround new stars. The process requires tens of millions of years and visible circumstellar material. The absence of such material, combined with the mass and distance of the observed planets, undermines the explanatory power of existing models. This calls into question not only the specifics of planetary genesis, but the reliability of the physical conditions assumed to be universal in star systems. These contradictions push inquiry toward a deeper level. If the universe is exhibiting coherent structures and entities that should not yet exist, then time itself must be reevaluated. The notion of linear time, inherited from classical physics and enshrined in the cosmological timeline, may not correspond to the actual temporal dynamics of the cosmos. Time, in this view, may be non-linear, stratified, or subject to variation, depending on spatial configuration or unknown universal parameters. This idea finds resonance in theories of cyclical cosmology, where time does not proceed from a singular origin, but oscillates through phases of expansion and contraction. In such models, the current universe is only the latest in a sequence of universal iterations. Each cycle may retain informational residues from its predecessors, creating patterns and configurations that appear prematurely formed or inexplicably aligned. These echoes could account for the structural anomalies observed by the James Webb Space Telescope. If galaxies, planetary systems, or gravitational architectures are, in some sense, recapitulations of previous cosmic iterations, then their presence is not premature, but inherited. The hypothesis that the universe retains a form of memory challenges the reductionist framework that has dominated modern physics. Memory, in biological terms, is an emergent property of complex systems. In cosmological terms, it would require a substrate capable of informational storage and transmission across epochs. This substrate cannot be located in matter or energy alone, both of which degrade or transform. It must be located in structure itself, in the relations, proportions, and topologies that endure through cosmic cycles. This conception aligns with certain interpretations of quantum information theory, which posit that information, not matter or energy, is the most fundamental constituent of reality. The implication here is profound. It means that the universe may not be a blank slate upon which randomness writes arbitrary configurations, but a structured field in which informational constraints shape the emergence of phenomena. The appearance of perfect symmetry, repeated geometric arrangements, and structured anomalies would then be manifestations of an underlying informational order. Such a framework would radically reconfigure our understanding of causality, randomness, and lawfulness. It is in this context that the rhythmic infrared signal detected from the constellation Fornax assumes its full weight. The signal's regularity, frequency, and persistence suggest a source that is not stochastic. While astrophysical phenomena can produce periodic emissions, such as pulsars, variable stars, or binary systems, the characteristics of this particular signal do not match any known category. Its wavelength, modulation, and non-radiative form imply a process that is not naturally emergent, but perhaps intentionally structured. The reticence of scientists to classify this as evidence of intelligence reflects the disciplinary boundaries of empirical science. Yet the possibility that the signal represents a form of non-human, perhaps non-biological intelligence, must be considered. Intelligence in this context does not imply intention, purpose, or consciousness in human terms. It implies the capacity to produce order, regularity, and communication through structured signals. Such a capacity could arise from processes or entities vastly different from life as we understand it. It could be the result of a hyper-advanced civilization encoding information across cosmic distances. It could be the byproduct of a previous universal cycle, leaving imprints in the fabric of space-time. Or it could be a property of the universe itself, a kind of reflexive structure capable of signaling its own transformations through informational shifts. This leads to a final consideration: the hypothesis that the universe is approaching a transition point in its physical laws. The concept of phase transitions in physics refers to abrupt changes in state, such as the transition from liquid to gas, or from normal conductivity to superconductivity. If the universe itself is a system subject to such transitions, then its laws, constants, and parameters are contingent rather than absolute. The James Webb Space Telescope may be capturing the preconditions of such a shift, an alteration in the behavior of particles, forces, or space-time itself. A cosmic phase transition would not necessarily be catastrophic. It might unfold silently, imperceptibly, altering the structure of reality without explosive events. Time might stretch or contract. The values of constants might drift. The geometry of space might recalibrate. Such changes would elude detection by existing instruments, designed for a universe assumed to be stable and law-governed. Yet they would alter the conditions of possibility for all subsequent observation and theory. The psychological and philosophical consequences of this possibility are immense. If the laws of physics are themselves subject to change, then science becomes a historical enterprise, its truths valid only within temporal boundaries. This would require a new epistemology, one that acknowledges the temporality of knowledge and the contingency of laws. It would also necessitate a metaphysics capable of accommodating variability at the foundational level, a metaphysics not of fixed substances or eternal truths, but of dynamic structures, transformations, and thresholds. In such a framework, human cognition is no longer the neutral observer of a stable cosmos. It becomes an embedded, evolving function of the universe's own transformations. Our instruments, our theories, and even our categories of thought are conditioned by the epoch in which they arise. We are not outside the system we study. We are expressions of it. As the universe changes, so do our capacities to understand it. This recognition imposes a duty of epistemic humility. It requires the scientific community to question its deepest assumptions, to remain open to paradigmatic upheaval, and to resist the institutional inertia that defends established models against anomalous data. The history of science is replete with revolutions, moments when the accumulation of anomalies forced a radical rethinking of principles. We may be living through such a moment now. To navigate this transition, a broader intellectual alliance is needed. Physicists, cosmologists, philosophers, and information theorists must collaborate to build models that can account for structural recurrence, informational resonance, and law variability. Theories of everything must be abandoned in favor of theories of epochs, descriptions of how the universe behaves under specific conditions, with the recognition that those conditions may themselves evolve. This is not a retreat from science, it is its maturation. Science must move beyond the aspiration to finality and embrace its role as an ever-adapting framework for understanding a reality that exceeds any singular formulation. The discoveries of the James Webb Space Telescope are not the end of explanation. They are the beginning of a deeper, more complex engagement with the nature of the universe. In this process, a new form of inquiry must emerge, one that integrates empirical observation with philosophical analysis, one that seeks not certainty, but coherence, not prediction, but understanding. This form of inquiry must be willing to ask what has previously been unaskable, not only what the universe is, but whether it is, in some sense, aware. The hypothesis that the universe could, in some form, be aware, or at least exhibit characteristics of informational reflexivity, challenges the most deeply held convictions of the materialist worldview. In classical scientific epistemology, awareness is a property exclusive to organized biological systems. It emerges from the complex interaction of neurons, biochemical signaling, and adaptive evolutionary pressure. This presumption, however, rests on the assumption that mind is reducible to matter, that subjectivity is a byproduct of physical complexity, and that consciousness is an epiphenomenon rather than a fundamental aspect of reality. Recent findings in cosmology and quantum physics increasingly undermine this framework. The idea that the universe might operate according to principles that involve not only material causation but also informational consistency leads to reconsiderations of the status of consciousness itself. When patterns in galactic structures repeat across billions of light-years and reveal geometries not accounted for by probabilistic modeling, the interpretation cannot remain within the boundaries of mechanistic determinism. Such patterns may not be accidental. They may suggest an underlying structure of coherence, a grammar of space and time that behaves less like an inert matrix and more like an intelligent system encoding, processing, and perhaps responding to information. This is not to anthropomorphize the universe. It is not to suggest that it possesses intention or purpose in any teleological sense. Rather, it is to propose that the structural regularities, signal-like patterns, and recursive phenomena observed may be indicative of a self-organizing principle, a form of proto-intelligence that does not require consciousness as humans understand it, but nevertheless entails a dynamic relation between information and structure. To explore this idea rigorously, one must engage with the work of theoretical physicists and philosophers who have proposed models of reality based on informational ontology. In these frameworks, information is not derivative of matter. It is the substrate from which matter and energy emerge. From the perspective of digital physics, for example, the universe is akin to a computational system where physical laws are algorithmic constraints and particles are expressions of logical relations. Such a model implies that what we perceive as material events are manifestations of deeper, non-material rules, code that structures the unfolding of phenomena. In this view, when the James Webb Space Telescope captures a gravitational lens so perfectly circular that it exceeds all models of random alignment, it may be observing an output of this deeper code, an invariant relation that maintains its form across vast distances and epochs. When the telescope reveals galaxies forming at times when only diffuse gas should exist, it may be witnessing the operation of a system where temporal constraints do not align with thermodynamic assumptions. And when it detects infrared signals that repeat with mechanical precision, it may be intercepting a function of this universal logic, a recursive output of informational fields that transcend localized physical interactions. The philosophical tradition most aligned with these insights is that of process philosophy, particularly in the work of Alfred North Whitehead. In contrast to substance metaphysics, which holds that reality is composed of enduring things with intrinsic properties, process philosophy asserts that the fundamental constituents of reality are events, happenings defined by their relations and becoming. In such a model, the universe is not a collection of objects, but a web of interrelated processes that instantiate patterns of order and novelty. This approach resonates with the implications of cyclic cosmology and informational theory. The universe, rather than being a static arena in which events occur, is itself an evolving event, a processual reality that exhibits order through repetition and novelty through mutation. The existence of similar galactic formations across regions separated by billions of light years and eons of time becomes intelligible not as coincidence, but as expressions of recurring processes that are governed by informational attractors. These attractors are not physical forces, but constraints on the field of possibility, patterns that the universe tends toward due to the structure of its own becoming. In such a framework, memory is not stored in substrates, but in the reactivation of patterns. The universe remembers not by archiving, but by repetition. The re-emergence of specific galactic configurations, the recurrence of signal patterns, and the symmetry of gravitational distortions are not evidence of causality in the classical sense, but of resonance, of past configurations influencing present dynamics through the consistency of structural relations. This conception has implications that extend far beyond astrophysics. It suggests that knowledge itself must be reinterpreted. Scientific knowledge has traditionally aimed at universal, timeless truths, laws that apply always and everywhere. But if the universe evolves, not just in content, but in form, then laws themselves may be epochal, valid within specific historical configurations, but subject to transformation. The constancy of the speed of light, the strength of gravitational interaction, the value of the fine structure constant, all may be parameters that shift as the universe undergoes phase transitions. These transitions could be driven by the internal dynamics of the universe, by informational thresholds, or by conditions yet unrecognized. The James Webb Space Telescope may be observing the signs of such a transition, not through violent events, but through discrepancies that reveal the limits of current theory. A planet orbiting an impossibly young star, a galaxy where none should be, a gravitational ring more perfect than randomness allows. Each of these is a deviation, a signal that the assumptions guiding interpretation no longer apply. The accumulation of such deviations marks the onset of epistemological crisis, and it is precisely at the moment of such crisis that the possibility of new understanding emerges. The history of science has passed through such thresholds before. The Ptolemaic system collapsed under the weight of observational inconsistency. Newtonian mechanics was superseded when it could no longer explain electromagnetic phenomena and relativistic effects. In each case, the new model was not merely a refinement of the old, but a reconfiguration of the conceptual apparatus. Categories were redefined. Space and time became dynamic. Causality was replaced by probability. We are now at a similar juncture. The anomalies documented by the James Webb Space Telescope are not isolated errors. They are indicators of conceptual obsolescence. To move beyond this impasse, science must reintegrate with philosophy. It must acknowledge that its theories are not neutral descriptions, but interpretive frameworks. And it must become conscious of its own metaphysical commitments, the assumptions about time, causality, matter, and order that structure its models. Without such awareness, theory becomes dogma, and data becomes noise. With such awareness, however, a new phase of inquiry can begin, one in which science does not seek closure but openness, not finality but process. In this new phase, the question of life must also be reconsidered. If intelligence can manifest not only in neurons, but in patterns, not only in organisms but in galaxies, then the category of life must be expanded. Life would no longer be defined by replication, metabolism, and evolution, but by the capacity for pattern generation, information processing, and adaptive structuration. From this perspective, the universe itself could be seen as a living system, not in the metaphorical sense, but in the sense that it exhibits the properties associated with autopoiesis, the self-generation, and maintenance of structure. Such a view aligns with certain strands of systems theory, cybernetics, and holistic biology. It suggests that intelligence and life are not rare exceptions within an inert cosmos, but expressions of the universe's intrinsic capacities. The James Webb Space Telescope, by expanding our perceptual horizon, may be revealing that intelligence is not localized, but distributed, not rare but pervasive, not incidental but structural. This reframing has implications for our understanding of extraterrestrial life as well. The traditional search for life beyond Earth has focused on biological markers, water, oxygen, carbon compounds. But if life can manifest as pattern, as signal, as structure, then the scope of inquiry must expand. The rhythmic signal from fornax may not be the product of a civilization as we understand it, but of a systemic intelligence operating at a scale and modality beyond current categories. It may be a residue, a broadcast, or a harmonic, an artifact of a logic that expresses itself through rhythm and repetition, rather than language or intention. Such an interpretation requires not speculation, but methodological innovation. It demands new models of detection, new frameworks of interpretation, and new metaphysical humility. The refusal to consider such possibilities on the basis of their incompatibility with existing theory is not skepticism, but dogmatism. True skepticism requires openness to the unknown, to that which resists categorization, to the data that defies expectation. In light of these reflections, The role of humanity in the cosmos must also be reassessed. If the universe is a living, intelligent system, then human consciousness is not an accidental byproduct, but a localized expression of a universal process. This does not entail anthropocentrism. It entails participation. Humans are not observers of a separate reality. They are co-constitutive elements in its unfolding. Our theories, perceptions, and inquiries are not passive representations, but active constructions, ways in which the universe becomes aware of itself through its own manifestations. This perspective is not mystical, but rational. It follows from the empirical anomalies and theoretical insights accumulated through rigorous observation and critical analysis. It requires no appeal to supernatural agency or transcendent purpose. It requires only the recognition that matter, energy, and information are not separable domains, but aspects of a unified process, and that this process includes consciousness, structure, and transformation as intrinsic features. From this vantage point, the James Webb Space Telescope becomes more than an instrument. It becomes an organ of perception, an extension of the universe's own reflexivity. Its data are not external facts, but internal revelations, signals from the depths of space-time that inform and reconfigure our understanding. The telescope sees not for us, but as us. It is a technological embodiment of the universal capacity to reflect, to organize, to signify. This is the task before us now, to interpret what we see, not in terms of outdated paradigms, but in terms of what is emerging, to listen to the signals, not as noise or anomaly, but as the speech of a reality more complex, more dynamic, and more intelligent than we have previously imagined. To recognize that knowledge is not the accumulation of facts, but the transformation of understanding through engagement with the unknown. The intellectual obligation imposed by the current cosmological anomalies is not limited to the domain of observational astrophysics. It extends into the fundamental structure of knowledge itself, compelling a re-examination of what it means to know, to explain, and to comprehend. The James Webb Space Telescope's revelations do not merely enlarge the catalog of known entities, they alter the conditions under which intelligibility is possible. This demands a revision of epistemology, not in the form of new heuristics or methodologies, but at the level of foundational assumptions. Traditional scientific epistemology operates on the presumption of an objective reality, governed by stable laws and accessible through empirical observation and logical inference. This model is predicated on two intertwined principles: ontological realism, the belief that a reality exists independently of observers, and epistemic objectivism, the conviction that knowledge can approximate this reality through neutral, reproducible procedures. However, the emergence of phenomena that evade classification, that contradict theoretical expectations, and that suggest the variability of physical laws undermines both pillars. When early galaxies are observed in defiance of formation timelines, or when a signal of unknown origin is detected with rhythmical consistency from a sector of deep space, the standard framework encounters its limitations. These are not errors to be corrected or uncertainties to be minimized. They are indicators of conceptual rupture, of the inadequacy of existing ontological and epistemological commitments. They require not more data, but different thought. This rupture opens a path toward a post-Cartesian epistemology, one that abandons the subject-object dichotomy in favor of relational coherence. In this framework, knowledge is not the representation of an independent world by an autonomous mind. It is the co-emergence of observer and observed through interaction. This view finds precedent in quantum mechanics, where measurement does not merely reveal but constitutes the state of a system. It also resonates with the phenomenological insight that perception is always situated, embodied, and historically contingent. Applying this to cosmology, one must recognize that the images received by the James Webb Space Telescope are not raw data awaiting interpretation. They are already configured by the structure of the instrument, the assumptions of the mission design, and the interpretive frameworks of the scientific community. The galaxies seen are not things in themselves, but phenomena as measured, shaped by wavelengths selected, filters applied, and models presumed. This does not invalidate the data, it situates it. It reveals that knowledge is an event, not a mirror. In light of this, the task of cosmological understanding becomes one of interpretive synthesis rather than deductive modeling. It requires the integration of multiple forms of inquiry: empirical, theoretical, philosophical, and even historical. For instance, the conceptual history of space and time must be brought into dialogue with current anomalies. The Newtonian concept of absolute space, the Einsteinian model of curved space-time, and the quantum conception of indeterminate location all offer partial truths, each valid within its domain of application. The challenge is to develop a meta-theory that accounts for their contextual validity while addressing the emergent phenomena that exceed them. This meta-theoretical project must also incorporate insights from the philosophy of science, particularly the recognition that scientific paradigms are not static, but historical. Thomas Kuhn's analysis of scientific revolutions demonstrated that periods of normal science, characterized by problem-solving within a given framework, are punctuated by crises where anomalies accumulate and the existing paradigm can no longer accommodate them. What follows is not a linear progression, but a rupture, a gestalt shift in which the very meaning of observation, explanation, and evidence is transformed. We are arguably in the midst of such a shift. The anomalies observed by the James Webb Space Telescope are not peripheral inconsistencies but central contradictions. They affect the origin of the universe, the formation of structure, the nature of gravity, and the possibility of extraterrestrial communication. They force a confrontation with the limits of the prevailing paradigm. Continuing to interpret them within the current framework risks rendering them unintelligible. A new conceptual orientation is necessary. This orientation must be capable of accommodating the possibility that the universe is not a static object, but a dynamic process, that its laws are not fixed but emergent, that its structure is not given but evolving, and that intelligence, structure, and information are not separable categories but interwoven aspects of a single reality. In such a context, the distinction between the physical and the informational, between the material and the formal, dissolves. This dissolution calls for a new metaphysics, one not grounded in substance or causality, but in relation and transformation. Such a metaphysics would see the universe not as a machine, but as a field of becoming, not as a container of objects, but as a generative matrix of events. In this view, what the James Webb Space Telescope observes are not things but processes, processes that instantiate pattern, recurrence, and novelty in configurations that challenge linear, mechanistic interpretation. Consider the implications of this for the interpretation of the so-called Einstein ring. Under traditional analysis, it is a gravitational lensing effect, a product of the warping of space-time by a massive object. But when such a ring exhibits a level of symmetry that exceeds probabilistic expectation, it forces reconsideration. Is the ring merely an optical artifact of mass distribution, or is it the manifestation of a deeper geometric principle, an attractor toward which certain configurations tend? The latter would imply that the universe not only allows but favors certain forms, that symmetry is not incidental but constitutive. This would align with theories in morphogenetic fields and complexity science, where systems evolve toward states of higher coherence. In such theories, Order is not imposed from without, but emerges from within, through the interaction of parts and the feedback of information. The universe, then, is not governed solely by entropic degradation, but also by negentropic organization. It does not merely decay, it organizes. And this organization is not random but structured, perhaps according to laws we do not yet comprehend. To study such a universe requires a science that is itself dynamic, reflexive, and integrative. It requires tools that can detect not only particles and waves, but patterns and signals. It requires models that are not merely predictive, but generative. Models that can simulate the emergence of form from fluctuation, the evolution of coherence from chaos. And it requires a philosophy that can interpret these models without reducing them to mechanistic schemas. This is the frontier we now face. The James Webb Space Telescope has pushed our observational capacity to a level where the universe's deeper structure is becoming visible. Not its content alone, but its form. Not its phenomena alone, but its principles. What remains is the interpretive labor of understanding what these structures mean, not within old categories, but through new conceptual frameworks. One such framework is that of second-order cybernetics, which emphasizes the role of the observer within the system. In this model, knowledge is not about an independent reality, but about the interaction between system and observer. The observer's categories, tools, and expectations shape the observations. This reflexivity means that science is not outside the universe, but inside it, a mode of participation in the process it studies. This insight parallels certain developments in quantum physics and cognitive science, which increasingly recognize that the observer cannot be separated from the observed. Applied to cosmology, this implies that our instruments, both technical and conceptual, are themselves events within the cosmic process. The James Webb Space Telescope is not just a passive receiver of light. It is an active participant in the universe's process of self-disclosure. What it reveals depends on how it is configured, how its data are processed, and how its findings are interpreted. The cosmos is not speaking in a human language, but it is capable of being read, and our reading transforms what is read. This leads to a further implication: the necessity of epistemic responsibility. If knowledge is co-constructed, then the manner in which we inquire matters. The models we construct, the questions we ask, and the interpretations we propose shape the future of inquiry. They determine what is seen and what is excluded, what is valued and what is dismissed. In this context, to persist in outdated paradigms in the face of contradiction is not merely error, it is neglect. Epistemic responsibility entails openness to revision, commitment to coherence, and humility before the unknown. It recognizes that the universe exceeds our current categories, that understanding is provisional, and that insight requires transformation not only of models, but of minds. It also requires the willingness to engage across disciplines, to integrate insights from philosophy, systems theory, information science, and cognitive studies into a unified pursuit of intelligibility. This interdisciplinary synthesis is not a luxury, but a necessity. The challenges posed by the James Webb Space Telescope AS data cannot be resolved within the silos of specialized knowledge. They require holistic thinking, capable of connecting the micro and the macro, the empirical and the conceptual, the quantitative and the qualitative. Such thinking is rare, but it is the condition for progress at the edge of knowledge. At this edge, certain questions become unavoidable. What is the origin of the laws that govern the universe? Are they eternal, or do they evolve? Is the universe a singular event or a cyclic process? What is the status of information, and how does it relate to matter and energy? Is consciousness an emergent property, or is it a fundamental feature of reality? These are not speculative indulgences. They are the unavoidable horizon of current inquiry. The data compels them. The anomalies demand them. It is within this context that two actions must follow, not as marketing gestures, but as necessary steps for a collective response. First, the community of inquiry, scientific, philosophical, and interdisciplinary, must commit to collaborative frameworks that are not constrained by disciplinary borders. Second, the public must be engaged with the seriousness and depth of these findings. A new cosmological understanding is not a matter of academic refinement, it is a civilizational event. It alters our self-conception, our ethical frameworks, and our existential horizons. At this civilizational juncture, what is required is not only the expansion of scientific methodology, but the reconstitution of cosmological imagination. The revelations yielded by the James Webb Space Telescope function not merely as empirical anomalies, but as epistemological provocations, compelling a collective reassessment of how reality is conceptualized, how knowledge is structured, and how the human species situates itself within the totality of cosmic processes. The theoretical edifice of modern cosmology, built on the pillars of general relativity, quantum field theory, and the inflationary model, is undergoing an observable destabilization. This destabilization does not indicate the collapse of rational inquiry, but the necessity of its evolution. The current model has proven extraordinarily productive in explaining a wide range of phenomena, from the cosmic microwave background radiation to the large-scale structure of galaxies, from gravitational lensing to particle interactions at high energies. However, when new observations present data that defy integration within this structure, when galaxies appear too early, when exoplanets orbit in contradiction to formation theory, when symmetrical rings and repeating signals persist without natural explanation, the framework must either mutate or be superseded. It is the duty of rational inquiry to prioritize coherence over fidelity to legacy models. This demand is not simply theoretical. It carries implications for every domain in which cosmology exerts influence, from physics and philosophy to anthropology, ethics, and even political economy. The cosmology a civilization embraces underwrites its orientation toward knowledge, its valuation of meaning, and its allocation of resources. In this sense, cosmology is not a domain isolated within academia, but the deep structure of cultural and intellectual life. When the cosmological model changes, so too must the structures built upon it. If the universe is no longer a machine governed by immutable laws, but a living process characterized by emergent patterns, recursive structures, and potential informational reflexivity, then the entire architecture of knowledge must shift accordingly. This new architecture would recognize that the universe is not fully intelligible through reductionist explanation, that its intelligibility is provisional and situated, and that its deepest properties may only be revealed through models that accommodate contingency, nonlinearity, and interdependence. The James Webb Space Telescope, in transmitting data that breaks with predictive expectations, has inaugurated this transformation. The theoretical vacuum left by the failure of current models to explain observed phenomena cannot remain unfilled. If science does not provide a new explanatory framework, pseudoscience and metaphysical speculation will inevitably occupy the void. The imperative, therefore, is twofold. First, to resist the urge to suppress anomalies in favor of theoretical continuity. Second, to engage in conceptual reconstruction with intellectual honesty and interdisciplinary rigor. The initial phase of this reconstruction must begin with the redefinition of key cosmological concepts. Time, for instance, must no longer be assumed to be linear, homogeneous, or absolute. The emergence of early galaxies, as well as the theory of cyclic cosmology, suggest that time may be layered, recursive, or generated by structure rather than preceding it. Space, similarly, may not be a neutral container, but a dynamic field conditioned by information, structure, and relational tension. Matter and energy may not be the primary constituents of reality, but expressions of deeper informational fields. This move toward an informational ontology finds support in developments in quantum gravity, string theory, and computational metaphysics. The notion that space-time itself may be emergent, from quantum entanglement, informational networks, or topological structures, recasts the foundational elements of physics as derivative phenomena. In this paradigm, what appears as gravitational curvature or mass energy density is the macroscopic projection of sub-physical informational relations. Observations of anomalous gravitational effects, such as those that no longer require dark matter for explanation, could be understood as evidence of the insufficiency of our current mathematical formalism to describe these underlying structures. Another conceptual redefinition pertains to the role of the observer. As second-order cybernetics and quantum mechanics both attest, the observer is not extrinsic to the observed, but co-constitutive. The James Webb Space Telescope, as an apparatus of observation, embodies this principle. It does not simply detect light, it constructs a data environment through which specific kinds of information become accessible, while others remain occluded. This insight mandates a reflexive stance in cosmological interpretation, one in which the process of knowledge production is itself acknowledged as part of the phenomenon under study. From this position, cosmological inquiry becomes an ethical as well as an epistemic endeavor. The responsibility of interpreting the universe extends beyond accuracy to include fidelity to complexity, openness to uncertainty, and responsiveness to the implications of 1S model for how humanity understands itself and acts within the world. The image of the universe that science constructs is never neutral. It either reinforces or disrupts cultural assumptions about hierarchy, order, value, and possibility. A cosmology that centers mechanism and randomness promotes one kind of ethical orientation. A cosmology that reveals recursion, structure, and the possibility of intelligence beyond the human promotes another. In this context, the possibility of extraterrestrial intelligence, as indirectly suggested by the rhythmic infrared signals detected by the James Webb Space Telescope, demands rethinking not only biological definitions of life, but philosophical definitions of intelligence. Intelligence need not be personal, conscious, or technologically advanced in the terrestrial sense. It may be systemic, structural, or emergent. What matters is not resemblance to human cognition, but the capacity for pattern, response, and coherence. This broader definition opens the conceptual space for considering that intelligence may be distributed across cosmic structures, that it may manifest not as individual agency, but as the orchestration of complexity in a non-random manner. The refusal of mainstream scientific institutions to entertain this possibility reflects a deeper epistemological conservatism. The dominant model of intelligence as exclusively biological, intentional, and carbon-based arises from anthropocentric bias and disciplinary inertia. But as history shows, explanatory frameworks that resist revision in the face of contradiction eventually become obsolete. The patterns, signals, and symmetries observed by the James Webb Space Telescope are not claims of intelligent life. They are invitations to rethink what constitutes intelligence in the first place. To engage with this invitation requires a shift from hypothesis testing to pattern recognition, from prediction to interpretation. It requires not abandoning the empirical method, but expanding it, making room for modes of inquiry that do not reduce complexity to variables, that allow for emergence, that recognize that some phenomena are meaningful not because they can be replicated under laboratory conditions, but because they reconfigure the conditions of replication itself. A signal that repeats over billions of years is not an experiment. It is an event of meaning on a cosmic scale. The same applies to the detection of gravitational geometries that defy statistical randomness. These structures cannot be understood through traditional cosmological models. They suggest an alternative geometry, perhaps not Euclidean or Riemannian, but topological, fractal, or recursive. The mathematical tools for modeling such structures exist, but are underutilized in mainstream astrophysics. To mobilize them requires transdisciplinary integration, where mathematicians, physicists, computer scientists, and philosophers collaborate in constructing models that are not only formally consistent, but conceptually generative. Within this framework, the role of public engagement becomes crucial. The findings of the James Webb Space Telescope are not arcane technicalities. They are events of epistemic rupture, capable of transforming how humanity conceives of its origin, its environment, and its future. Therefore, public discourse must rise to the level of the data. Popular representations of science must cease to function as instruments of stabilization and begin to function as instruments of transformation. This entails a change in the language of science communication, away from simplification and toward intellectual provocation, away from consensus maintenance and toward participatory questioning. To facilitate this shift, institutions of science must foster environments of risk-taking, intellectual diversity, and critical reflection. This includes funding theoretical work that challenges orthodoxy, supporting cross-disciplinary collaborations, and encouraging researchers to pursue questions that resist easy answers. The cosmological transition initiated by the James Webb Space Telescope is not only observational, but institutional. If the institutions of science are not structurally capable of responding to paradigm-level data, they will be bypassed by cultural movements less bound by methodological constraints. This is not a warning, it is a call to action. The responsibility of science is not to preserve the status quo, but to follow evidence wherever it leads, even, and especially, when it leads beyond existing models. The integrity of inquiry depends on its willingness to relinquish certainty in pursuit of understanding. The anomalies observed by the James Webb Space Telescope do not undermine science. They vindicate its core principle, that knowledge must adapt to reality, not the reverse. In this spirit, a new orientation toward cosmology is required, one that integrates observational fidelity with philosophical depth, that treats anomalies as openings rather than threats, that constructs models not as final explanations, but as provisional maps of a terrain that remains radically open. This orientation does not abandon rigor, it deepens it. It does not forsake explanation, it redefines it. It does not retreat into mysticism, it advances into complexity. The universe observed by the James Webb Space Telescope is no longer the one described by early modern science. It is older, stranger, more ordered in some respects, more chaotic in others. It exhibits structure before time allows, signals without source, patterns without precedent. These are not puzzles to be solved within existing frames. They are signs of a reality whose intelligibility demands a new mind, an epistemology that is adaptive, a metaphysics that is relational, a science that is reflexive. Such a transformation is not instantaneous. It unfolds across decades through the accumulation of insights, the reformulation of principles, and the gradual construction of a new coherence. But it begins now, with the courage to take anomalies seriously, the discipline to pursue complex explanation, and the vision to see in the cosmos not a closed system of laws, but an open horizon of becoming. What comes next cannot be predicted. It can only be invited, encountered, and interpreted. The universe, through instruments of our own design, is telling us something, not in words, but in light, in rhythm, in form. The responsibility to listen is ours. Stay engaged. What has been seen cannot be unseen. What has been revealed is only the beginning.